Welcome back to the deep dive. We're opening up the technical manuals again today, and we're focusing on a machine that's been generating a lot of conversation.
A lot of conversation.
We are talking about the A321XLR, but before you just roll your eyes and think, great, another A320, we need to stop right there.
Because if you treat this aircraft like just another A320, it will bite you.
That's the reality. We're
Yeah.
looking at the 321-200NY. That's the technical designation in the documents. And the cockpit looks familiar, but the physics underneath it have fundamentally changed.
They really have. We've pulled the high-lift system logic
Mhm.
from the DSC 27 section of the FCOM to really tear this apart.
And honestly, that NY designation feels appropriate because this is a new animal.
A completely new animal in terms of energy management. This isn't just a stretched fuselage.
No, not at all.
Yeah.
We're talking about a plane with transoceanic capability. The range is massive, which means the fuel load
Is massive. And when you operate an A321 at these higher weights, I mean, we're basically talking wide body weights on a narrow body frame.
So you can't just drag the aircraft around the sky like you might with a lighter A319 or a standard A320.
That's the core tension. The physics have shifted. On a lighter jet, you have excess power, less inertia. You can be a little sloppy, and the plane forgives you.
Right.
But the XLR has so much inertia, once that mass is moving, it wants to keep moving.
Which is why the engineers didn't just slap bigger fuel tanks on it. They actually reprogrammed the brain of the wing.
Specifically, the flight control unit logic.
Right. So our mission today is to decode that logic. We're going to look at three specific systems that really set the XLR apart.
Okay.
The Enhanced Takeoff Configuration ETOC, the Flap Load Relief Function FLRF, and the Alpha Speed Lock.
And this isn't just academic. Understanding these three is the difference between fighting the aircraft and actually flying it.
So let's start with that context. We mentioned weight. The XLR is heavy. How does that drive the need for all this new system logic?
Well, think about takeoff. You're at maximum takeoff weight. Maybe it's a hot day, high altitude.
You need every ounce performance you can get.
Every single bit. On a standard A320, the flap and slab positions are fixed. They're mechanical detents. You select config 1+F, the surfaces go to a set angle, and that's it.
It's a one-size-fits-all kind of approach.
Essentially. And for a lighter plane, that's fine. The margins are wide enough, but on the XLR, close enough just doesn't cut it anymore.
Especially for that second segment climb, right? Engine out scenarios.
That's it. To meet those regulatory requirements, you have to optimize the lift-to-drag ratio to a much higher degree.
And that leads us directly to the first system, ETOC, Enhanced Takeoff Configuration. I was reading DSC 273010, and it describes this as a function that automatically adjusts the configuration.
Yeah.
So it's not using fixed settings.
It is not. The lever in the cockpit still has the same clicks, 0, 1, 2, 3, full. But what the wing actually does when you select config 1 or config 2 is now variable.
How so?
The system looks at your takeoff weight, the temperature, your performance requirements, and it calculates the optimal deflection angle for the flaps and slats.
So on Tuesday, config 1 might mean the flats are at 18 degrees, but on Wednesday, with a heavier load, it might mean they're at 20 degrees.
Precisely. It's micro-adjusting the wing to squeeze out the best possible climb. It's brilliant, but it creates a really fascinating human factors problem.
The visual trap.
Yeah. I mean, imagine you're a captain. You've been flying A320s for 15 years. You've done thousands of walkarounds.
You know what that wing looks like.
You know exactly what that gap between the slat and the wing looks like. It's a
Exactly.
visual memory. You glance at it, your brain says check, and you move on.
But now on an XLR, that gap might be different.
It will be. So you walk around, the ETSC has set a slightly different angle for the weight. You look up, and your brain just goes, whoa, that's wrong.
And the immediate thought is mechanical failure.
The actuators are drifting. The sensors are bad. We've seen reports of pilots calling maintenance because the visual doesn't match their expectation.
And what about in the cockpit? Looking at the ECAM flight control page?
Same thing. Those little green triangles that show the surface position might not line up exactly where you're used to seeing them.
They won't.
And this is where the New York variant demands that new mindset.
Yeah.
You have to trust the ECAM. If it's green and says the config is valid, the system is doing its job. It's not broken. It's optimizing.
So the big takeaway for ETOC is the wing is smarter than your visual memory.
Don't second guess it unless you have an actual fault message.
Okay. So let's move to the other end of the flight. We've taken off, cruised, and now we're descending, and we're back to that inertia problem.
Yeah.
The XLR is a clean aircraft. It's aerodynamic,
Right.
and it's heavy. That sounds like a plane that does not want to slow down.
It is incredibly slippery.
Yeah.
If you're in a high-energy descent, maybe ATC keeps you high and fast and tells you dump it all at once, you are going to struggle.
And this is where pilots can get into trouble with the flap load relief function, or FLRF.
They can. Now, most modern jets have some form of load relief, but the way it kicks in on the XLR and what happens next, that's what's critical.
So set the scene for us.
You're on approach, you're a bit fast, but you throw out the flaps to config 2 or 3 to help slow down. But gravity and mass are working against you. The speed keeps creeping up.
You hit VFE, the max speed for that flux setting.
Right. The system sees you've exceeded VFE by a few knots. And to prevent airloads from damaging the flap tracks or causing an asymmetry, the FLRF activates.
And it automatically retracts the flaps to a lower setting.
Yep. The lever in the cockpit stays at 3, but the flaps on the wing physically move back to the 2 position.
Okay, so safety-wise, that makes sense. You save the wing. But what about the flight path? You're already fast and you've just lost drag and lift.
You're going to sink. Your descent rate increases. You might even accelerate more. But here's the real danger. The balloon.
This is the part that sounds like a roller coaster.
It is. So the system retracts the flaps. You, the pilot, see you're fast, so you pitch up or cut thrust to slow down. The moment your speed drops back below that VFE limit, the logic says, okay, safe now.
And it re-extends the flaps to match the lever position.
Instantly. And since flaps add lift, you suddenly get this huge, uncommanded spike in lift.
The balloons.
The aircraft balloons. You get a surge in G-load, the nose pitches up, and you can deviate way off your glide path. If you're on an ILS, that's an immediate unstable approach, probably a go-around.
I can see the temptation, though. If you know the system will protect the flaps, why not just ride that limit? Use FLRF as a kind of speed brake.
That is the forbidden fruit of automation. And the answer is twofold. First, from an engineering perspective, FLRF is an emergency protection.
Not a tool.
No. You are putting immense fatigue stress on the entire system every time you trigger it. But second, it's just terrible airmanship. If FLRF triggers, you have violated SOPs. You have mismanaged the energy of the aircraft. You are behind the jet.
You're reacting, not anticipating.
Exactly. And relying on a protection system to fly for you is a very slippery slope.
So if you see the flaps move on the ECAM without you touching the handle, that's not a cool feature. That's a warning shot.
It's a failing grade on your energy management.
Okay, let's talk about the third system. And this one, to me, seems like the most stressful scenario. The alpha speed lock.
This is the one that catches everyone off guard. It happens when your workload is highest.
We're talking a heavy takeoff or a go-around. You're low, you're climbing out, you want to clean up. Positive rate gear up. You get to your acceleration altitude and call for flaps 0.
You move the lever from 1 to 0. You expect the slats to retract so you can accelerate.
But nothing happens.
Nothing. You look at the PFD, you look at the ECAM, the lever position says 0, but the slats are still green. They're still hanging out.
And this is what you call the broken handle moment.
Yes. The psychological response is always to blame the hardware. The sensor is broken. I've seen pilots physically jiggle the handle thinking it's stuck.
But the plane is doing exactly what it was programmed to do.
It is. The alpha lock function is watching your angle of attack, your alpha and your airspeed. If you're heavy and slow or pulling back on the stick too aggressively, your angle of attack is high.
And the wing needs those slats at a high angle of attack.
It absolutely does. The slats keep the airflow attached to the wing. If you were to retract them while your alpha is that high, the airflow would separate. You would stall.
So the computer is saying, I don't care that you move the lever. If I retract these slats, we fall out of the sky. So I'm keeping them out.
That's the conversation happening inside the box. And you might see an ALOC message pulsing in cyan on the display. That's your clue.
But in the heat of that moment with the ground right there, you might not notice a little cyan text.
It often gets missed.
So here's the million-dollar question. Lever at 0, slats are out, the plane is protecting you. How do you fix it? Because your instinct near the ground is to pull up.
And that instinct is exactly what will keep you trapped in the alpha lock. If you pull up, you increase the angle of attack even more.
You're making it worse.
You're reinforcing the computer's decision to keep them out. You have to fight your survival instinct.
So what's the fix?
You have to push. You need to pitch the nose down, or at least stop pitching up to reduce the angle of attack. You have to let the aircraft accelerate. Feed the jet energy.
You have to prove to the computer that it's safe to clean up the wing.
And once that speed increases and the alpha drops below the threshold, the lock releases and the slats will retract automatically.
That requires incredible discipline. The controls aren't working, pitch down. That's a hard thing to wire into your brain.
It is. But it brings us back to that golden rule of the XLR. You are managing energy. The alpha lock is a symptom of low energy. The cure is always more energy.
It's fascinating how all three systems, ETOC, FLRF, and Alpha Lock, all come back to the aircraft, overruling the pilot to match the physics of the situation.
That's really the theme of this machine. With ETOC, it overrules your visual memory to optimize lift. With FLRF, it overrules your configuration to protect the structure.
And with Alpha Lock, it overrules your command to prevent a stall. It protects itself, and it protects you.
But only if you understand why it's doing it. If you fight the alpha lock by pulling back, you lose.
Okay, so let's synthesize this. If you're transitioning to the A321-200NY, what's the new definition of flying?
The old axiom is fly, navigate, communicate. It doesn't change. But fly now includes monitor and understand. You aren't just manipulating controls, you're putting in requests that the system validates against physics.
And because the XLR operates closer to the edge of those physics, the system's going to intervene more often than you might be used to.
Correct. You have to get comfortable with the idea that the wing is dynamic. It's alive. In a way, it's constantly changing shape.
And don't get trapped by the visuals. That idea that a pilot might write up a maintenance snag because the flap gap looks weird, that's kind of terrifying.
It just shows how reliant we are on patterns. We have to update our internal database. The XLR has new patterns.
Before we wrap, I want to pose a final thought. We're seeing this trend where the aircraft is becoming less of a tool and more of a partner, or maybe even a supervisor.
A supervisor is a strong word, but maybe not inaccurate.
I mean, if the plane is smart enough to calculate the perfect slat extension and smart enough to refuse a pilot's command that would lead to a stall, at what point does our skill set stop being about stick and rudder and start being purely about systems management?
It's the debate of the modern era. But I'd argue that understanding why the alpha lock engages requires more airmanship, not less. You need to understand aerodynamics better to fly the XLR well than you did to fly a Cessna, because the consequences of ignoring the physics are so much higher.
So we aren't just becoming button pushers.
No, we're becoming physics managers, energy managers. And on the XLR, energy is everything.
A fitting place to land. For everyone listening, check your manuals, look up DSC-27, and respect that NY designation. It's a beast, but if you understand it, it's a magnificent one to fly. Thanks for joining us on the Deep Dive.
Safe flying, everyone.